Hello folks, today we're talking about the inverse of a matrix, material from 2.2. So as usual, I'll give you some motivation here. This is motivation from probably elementary school. So given a number, let's say, I don't know, say 5, can we solve, the equation or whatever you want to call it, 5 times something equals 1, right? So I want to know, is there a number here that I can put that multiplies 5 to 1, say? And of course, I can take this to be 5 to the minus 1 or 1/5, right? And so in this sense, we say that 5 is invertible because it has an inverse. And in fact, all numbers are invertible. Well, but not quite all of them, right? All numbers are invertible except the number 0, right? So, of course, I cannot solve 0 times something equals 1. That's not going to work, right? There's nothing I can put there to to solve that. So what we want to do is kind of extend the story to matrices today. So how does this look? How does this look, the story, in the world of matrices? Okay, and that's kind of what we're going to address today. So what I first need to do is, what are the players going to be? So I know what matrix multiplication is. What I don't quite know is what is 1. So what plays the role of 1? Well, remember, 1 is the number that multiplies any number to itself. And let me just give a definition. So define IN. This is going to be the n by n matrix given by, I'll just write this out in a picture. So it's got 1s down the diagonal. So everything down the diagonal is 1. And I have 0s everywhere else. Okay? So if you like, this has, has columns. So the first column, right, is what we call E1. The second column is going to be, 0, 1, 0, 0, 0. That's going to be E2, etc. So it's got n columns, and they're the n basis vectors that we've been talking about. So this is called the, n by n identity matrix. And why is it called the identity matrix? Well, the fact is that if A is any n by n matrix, then if I take A times IN, that's the same as IN times A, which is A. So I think I'll let you prove that in general, but just for example, if you took, I don't know, 1, 2, 3, 4, 5, 6 times 7, 8, 9 times I3, which is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Right, this is I3. Then what do you get? Well, you get a 3 by 3 because I've taken 3 by 3 times 3 by 3. And notice that when you look at any entry, right, so for instance here, what I'm going to do is I'm going to take that first row, first column, and what do I pick up? Well, I only pick up that first entry, 1 times 1 plus 0 plus 0, right? So that's 1. If I go here, this would be the first row, second column. So when I do 1, 2, 3, and 0, 1, 0, I only pick up that 2. I don't know, maybe I'd look at the third row, second column. So here I'm taking 7, 8, 9, and 0, 1, 0, and again I only pick up that 8. And so what you're getting is, in fact, just the matrix you started with. Okay, so this is going to be the, this identity matrix will be the sort of like the 1 of the matrix world. And so our definition then will be, the main definition of the day, is that an n by n matrix, A, is said to be invertible, or is called invertible, if, so just like over here, let me just kind of motivate this for a second. So we said that 5 was invertible because I could put something here to multiply to 1, right? So what we're going to do is the same thing here. Is we'll say a matrix is invertible if there exists an n by n matrix C, such that the same thing happens. If I take C times A, well, that's the same as taking A times C, and it gets me back to IN, the identity. Okay? So we say C is called the inverse matrix, or And we usually denote it, you know, just like we did before with numbers. I'm going to say A inverse. So instead of, you know, so C is the matrix, but, you know, when I realize that it's the inverse of A, I'll call it A inverse. Okay, so that's the, that's a kind of abstract definition. We're going to work with this now with a couple examples. Let me just start with a, kind of an example of how this works out. So if A is 2, 5, minus 3, minus 7, and I take C to be, I'm going to tell you what the inverse is. It's minus 5, 3, 2. I want you to show me that C is the inverse of A. Okay, so, if someone comes to you on the street with this matrix 2 by 2 matrix and they claim it's the inverse, it's relatively easy to verify that. You just compute. So to check, we just compute. Well, it's matrix multiplication, so it takes some work, but it's a doable thing. So I'm going to take A times C, which is, what is that? That's 2, 5, minus 3, minus 7, times minus 3, 3, minus 5, 2. This is going to be a 2 by 2 matrix, right? What's in the first entry? So I've got 2, so this entry here is going to be 2 times minus 7 plus 5 times 3. What is that? That's a 1. Maybe I'll just do this entry here. This is going to be, right now I use the second row first column. So this is minus 3 times minus 7 plus minus 7 times 3, which is 21 plus minus 21, that's a 0. And you can check that that's 1 and that's 0 as well. So indeed, you get the identity matrix. That's what we want, the I2. And I'm not going to go through this, but you can also check that C times A is I2 as well, I2, which is this thing here. Okay? And that's how you check that something's the inverse. You multiply, the two things out and you get the identity, then you're good. Now, I should say that the mystery here is how the heck did you come up with C? I mean, so you can't just guess this, and that's going to, well, actually the next slide I'll show you how to do in this case. In general, finding the matrix of the inverse of a matrix is, takes some work, and we'll talk about that. But here's the kind of cool thing for 2 by 2s. So here's an important fact. If A is a 2 by 2 matrix, right? And we know that if I take A times D, so those are the diagonals, minus B times C, which are the off diagonals, if this is non-zero, then A is invertible. So it has an inverse, and in fact, here's the formula for it. So what I do is I take 1 divided by that number, AD minus BC, and then that's a number that I'm going to scale a certain matrix by. I'm going to take D and A on the diagonal, so I swap the diagonals of the given matrix. And then I negate the entries off the diagonals. Okay, so that's an important fact. This actually, this gives you a formula for the inverse of a 2 by 2 matrix. This number you might have seen before, AD minus BC, so that's the product of the diagonals minus the off diagonals. This has a name, it's called the determinant. Determinant of A, and sometimes denoted, well, det A, or sometimes you put absolute value bars around A. There's different ways people use to denote this thing. So that's, like I said, that's a really nice formula for getting a determinant of a 2 by 2. Let me just do a quick example. Let's find the inverse of I don't know, let's see, well, A, let's say, is 3, 4, 5, 6. I should say, I didn't say this before, that if this thing is 0, then it actually is not invertible. And why this fact is true, I think we'll talk about this in our meeting, but for now, I'm just going to give you this as a fact. But how do you solve such a thing here? Well, we want to look at det A, which is, this 3 times 6 minus 4 times 5. This is the determinant that I care about. And indeed, that's minus 2, so this implies it is invertible. And our formula says that A inverse is going to be, 1 divided by that number times what do I do is I swap the diagonal entries, so this becomes 6, 3, and I negate the off diagonals. So if you want to just write that as a kind of a matrix without the number, that's minus 3, what is that, 2, 5 halves, minus 3 halves. And you can check now that if I multiply this guy by A, I'll get back the identity matrix. Okay, so yeah, so the next thing I want to do, like I said, we'll talk about kind of why this is true, and just let me note this now, write this down. If you had that AD minus BC equals 0, then the matrix A is not invertible, meaning there does not exist any inverse, okay? There's no matrix out there that'll multiply this thing to 1. Okay, so some important features of invertible matrix, there are many. Maybe the first one to notice is the following fact. Suppose we have an invertible matrix. N by n. I should say that, another thing to notice that in the world of matrices, the only time that I can talk about an invertible matrix is when you're a square matrix. So suppose you have an n by n invertible matrix, then for any vector b in, say, Rn, the matrix equation Ax equals b has a unique solution. So remember, that means one and only one solution. Okay, so this is again, we're going to list off a couple of, well, in this lecture and the next, we're going to list off a few important properties of invertible matrices, and this is one of the most important, but it's actually very easy to prove. So we want to solve Ax equals b, right? We know that this thing is invertible, so we can apply, that means there exists this inverse, A inverse. We're going to apply that to both sides to get A inverse times Ax equals A inverse times b, right? I'm just multiplying A inverse on the left on both sides, okay? Well, what does this mean? This is, A inverse times A, because I have this associative rule, equals A inverse b. But what is A inverse times A? That's the identity matrix times x, and that equals A inverse b. And you can check that the identity matrix, not only does it multiply matrices to what they were, but it also, when you multiply it by a vector, you also get what you started with. So this is saying that x is actually just this vector. So in other words, I'm telling you now what the solution is. Here is x. It's this vector, right? This is just a vector in Rn, and that's my answer. So not only do I know that it has a unique solution, in fact, this is the solution. Okay, and so the observation here, note that inverse matrices, well, the inverse, let me say it this way, the inverse of a matrix A provides a way to solve a system or equation Ax equals b. But I should say that, this is not usually how you want to solve a system. So I'll say, but, row reduction on just on the, the usual row reduction on the augmented matrix is usually much faster. So this is not actually a feasible or a sensible way to actually solve systems, but I'm saying that if you give me the inverse of a matrix, I can use it to solve systems because it actually tells me the solution. Okay, so next time we'll talk about some more important properties of inverses. So we'll see you then.